Welcome to the Cosmic Pie Podcast, Episode 14, Season 4.
Season 4, yeah.
We are broadcasting live from the campus of the University of North Dakota, and we have a brand new look today, Robert,
Right.
So we're testing a lot of things out. So would you like to explain maybe a little bit, so as a way of testing your mic, what's going on here?
Well, what's going on here is the room we were in has some environmental control issues. I'll leave it at that. And so we decided to try to switch our venue up and see if it would help us out as far as, environmental factors. So here we are.
So it is an experiment,
Right.
say nonetheless. But anyway, so we are broadcasting live. We have a live chat feature that should be running, but I don't presently see it. I don't know.
That's okay. I can see it.
Can you see it on your side?
I can see it on my side.
Okay, like I said, we're working the bugs out of all this new stuff now. Yeah. And for the look, by the way, that's not a fake background. This is in my office.
Right.
And you're getting sort of a 360-degree view almost, because one camera is pointed towards Robert, and then 180 degrees, the other camera is pointed towards
so
me.
we can actually look at each other straight instead of having to turn to
Look
the
off
side.
to the side and look at the board and up on the display monitor. We can actually see straight ahead. Disclaimer, Robert?
Well, the disclaimer is that the opinions and statements made are those of myself and Wayne. They are not indicative of the point of view or stance of the University of North Dakota, Department of Physics and Astrophysics, College of Arts and Sciences. Just us. You got to come at us.
Right,
So.
and just so to finish it off, don't forget, if you like this podcast, please give us one of these things. Let me rotate it too. You can go up and down, you can rotate, and then you can go this way. That's
Always the right hand
That's
rule.
row, pitch, I guess would be up and down, and yaw will be going that way.
Yep.
There you go. Roll, pitch, and out. We're 3 degrees of freedom in this podcast, you realize that.
There you go.
Now, the big news, which we're going to start off with, and by the way, just before I go to the first slide, we also have a podcast then uploaded on Spotify the next day. So if you rather see it in that environment, please feel free to do so. So let's start with the big news. We'll go with our first slide. And that, of course, is the news everywhere, worldwide, and essentially out to the moon and back, was the launch back last Wednesday now of the Artemis II mission to the moon. So we broadcast last on Tuesday, so it was the very next day. And I don't know about you, did you manage to see the launch live, Robert?
I didn't. I know it's going to disappoint a lot of people, but I'm really not a rocket guy. I appreciate these missions.
Okay, I have to interrupt you.
Okay.
Is it fair to call you a geologist?
Definitely, yeah.
So you're a rock guy.
I'm a rock guy.
But not a rocket guy.
Right.
Okay, I just want that for clarification. Continue, please.
I got into astronomy because I wanted to know how planets form. So I got then into rocks for my PhD run and ended up being second master's. So, yes, I'm a geologist as well as an astronomer.
Very nice. So the launch, as all of you I'm sure know, was successful last Wednesday, which is really cool. I mean, this is only the second time that vehicle has been launched.
Right.
And if you think back in the 1960s, which is, we always want to compare it to then because that was back in the Apollo program days, that when they launched the Saturn V, every one of the Saturn Vs, including the unmanned launches, were all successful, mostly. They all reached into the orbit. I mean, sometimes some of the engine would shut down a little early, but you had redundancy with other engines on board that would limp their way into orbit, but it mostly went almost perfectly. And I remember one of the major, reading about it back then, one of the problems that they had was something they call pogo. So it was this oscillation. The whole rocket would go up and down.
Okay.
In fact, I think the pogo effect, and they had it more in Saturn V, but they also had it in previous launches, like even the Titan for the Gemini launches.
Right.
If you listen to the audio, and thankfully now there are certain individuals online on YouTube. If you look do a search for, let's say, Gemini 5, you will actually come to their website where they transcribed all of the recordings.
Oh, wow. Okay.
And not only do you get the language, so you can read it yourself, but there are other places where you can listen to the audio from back in the mid 60s or late 60s and all of these flights. It's amazing what they've done now. And they digitized it, and they really, production value is incredible. So there's certainly a lot more ways of getting hold of those old missions and listening to what the air to ground communications and stuff. And they mentioned POGO. I was listening to one a couple of weeks back, one of the Gemini flights, and I don't remember which one it was. And they mentioned the term POGO. And it's like being on a pogo stick, right? That's where it comes from, jumping up. The whole rocket oscillates up and down. And as far as I remember, right, it has to do with the sloshing of the fluid inside the tanks on the rocket.
Okay, so it's not anything to do with the thrust of the engine.
I don't believe so. And in fact, I know a lot of the tanks had these baffles inside of them that would. In fact, don't they have that on like?
Yes.
You know what I'm getting at?
Yes.
Like a tanker on an 18-wheeler situation, right?
Right.
So the gas is not sloshing free back and forth. Because that can shake the vehicle, right?
And if it gets into a resonance mode, all of a sudden you're losing control, you're losing handling, because it's an oscillation that's growing larger and larger and larger.
No, that's a good point. It's the resonance that you worry about. It's like the bridge in Washington State that collapsed, right?
Gallop and Gertie. Yep.
Yes, because that used to swing back and forth, right, in the wind. And when you get the right resonance, then that can cause the complete, collapse of that bridge.
Right, and that's what the baffles are really about, is to keep. The bottom line, you now are instilling chaos into those oscillations so that they can't hit a resonance.
It's all fluid dynamics, Robert.
Absolutely. Beautiful stuff.
Really cool. So, and then going on to the next slide. So during the launch itself, so I watched it live. And one of the things I noticed, I'm going to nitpick. Sorry, play devil's advocate, whatever you want to call it. I'm going to nitpick. And the nitpicking is that the live coverage that I saw from NASA wasn't that great. In fact, I thought that the coverage of the high-definition cameras that they use for SpaceX launches and even Starship launches was actually superior to the Artemis II launch.
Doesn't surprise me.
In fact, if you watched it live or even a replay of the live version of it, you'll see a lot of times where how, I don't know, it's like this argument where many years ago, and it's not that many years ago, but to some people it would be, let's say a little more than a decade ago, let's say 20 years ago, for sake of argument, where the TV stations that come into your TV that you watch all through the coaxial cable. There's no streaming services.
Heck, we had the little screw in. It was free wire.
Well, don't say that.
Okay.
No, just kidding. I thought you were going to tell me you found a way to unscramble some stations.
Oh, no.
That was...
By the time I was in college, I knew how to do that. I never did it. It was against the rules, so I play by rules. Of course,
you would never do that. Now,
I had friends in the
hold on. Okay, let's change the subject. We only kicked off of YouTube for encouraging illegal activity or something. But yeah, so the TV signals that would come in were nice, crisp, and sharp. This is like the beginning into the first few years of high definition TV, for example. And then all of a sudden, it's like the TV goes and they switch the companies to like streaming over the internet.
Yes.
And now TV is lousy, at least for me, the company that I have, and I won't mention any names. I mean, if you're watching a sports event, it stops, or you lose, you get these large squares where you're you lost the full definition, and there's data dropouts and all this stuff, and you end up rebooting your modem, and there's way more of that, and and you're paying for each of these streaming services.
Yes.
And you're not getting the quality that we used to have for standard coax.
Right.
And that's my big gripe. It's almost like cell phones. Did you notice that? Before cell phones came out and were popular, the landlines were nice and clear and sharp. And then the first few years of cell phones, the reception was just terrible.
Terrible. And it's because they were trying to push everyone over into cell phones.
Yeah.
Who uses a landline anymore?
Well, that's it. I mean, you have to let the technology had to mature to a point. So I'm sure that's what will happen with our streaming services that we're getting now, right? And of course, a lot of people now don't even bother with that. They just watch stuff on YouTube or whatever they're doing, right?
Yeah.
But yeah, if you're getting streaming services now, at least around here, it can be an issue. But I'd expect that for the Artemis launch, you'd have the beautiful high definition, high bit rate.
I wouldn't have.
That was not the case at all.
I wouldn't have it all. and my justification and reason are something that I see commented on constantly. You know, we have cameras that can see these things, and why are bank cameras so terrible and NASA's cameras so terrible? Well, you're dealing with buying from the lowest bidder.
Yeah.
And anytime you're doing that, you're not going to get top-notch quality. You're going to get bargain basement.
So and here's an example of the slide that I'm showing you now. Sees a moment after the solid rocket boosters were ejected from the side of essentially the core stage.
Right.
I never saw this view live because at the moment, and it was one of those moments you're waiting for the solid rocket boosters to drop off, and that's a psychological thing for me and a lot of people my age who know that's just prior to the moment when the Challenger broke up. And so you're waiting for the solids to drop off because then a lot of the danger has passed. That's the feeling, psychological feeling that you have here.
And it's not a bad or wrong feeling.
No.
It's the honest truth.
Yeah. So we're waiting for the moment of solid rocket booster ejection, if you like, separation from the main core stage is something I was looking for. And when NASA showed it in real time, they were showing people sitting on lawn chairs watching the launch. You watch people watching the launch. And by the time they turned back to the live feed, it had already happened.
Right.
And so that was disappointing. So this slide that you see here is actually an image taken from, multiple cameras that download the data later. Right. And you get a lot of this high resolution images later on, not in real time in that sense. So that was a bit disappointing. Hopefully in the future they will improve that.
Here's hoping, but
SpaceX definitely, and even Blue Origin with their launches, their video feed I found was far superior to the one provided by NASA.
But when you're dealing with government, you're dealing with bargain basement. You're not dealing with top of the line.
Yeah, I mean, obviously you want to have high resolution images, which they do. I'm not arguing they don't.
Right.
In fact, you can go on YouTube now and you can see the launch replayed over and over and over again from like 10 different cameras. Because if something goes wrong, they want those high definition, really fast frame cameras to tell them, at least maybe to help into finding what went wrong.
Right, but that isn't for watching.
No, that's not real-time viewing.
Right.
Not at all. So the next slide is another one of these. We knew when the escape tower, so that's the part where when they get launched, the astronauts on board the Orion space capsule cannot see outside. The windows are covered up by this object here. And this is meant to pull the Orion spacecraft away from the rest of the rocket in case the rocket's on the verge of blowing up when things go wrong.
Right.
And so definitely you need that. And that stays with the rocket until you're, several minutes later, it's after the solid rocket booster sort of separation.
And then the pyro bolts blow and the rocket kicks in and flies it away.
Well, yeah, and as soon as this separated, then you have a view. In fact, the commander of the flight radioed down something like, what a view, what a great view, because now you can see out the window.
Yeah.
So you knew it had separated, but you really didn't see that in real time. So this is a still of an onboard camera that was looking up the stack, up towards the front of the rocket, and it captured this view of essentially the escape tower separating from the vehicle, from the SLS rocket. So this is an amazing view. So it's beautiful, and you see the Earth obviously in the bottom part as well. Great view.
Absolutely. I love it. Yeah.
Now, of course, Earth takes the attention right away because you are closer to Earth than you are to the moon, even though this flight, as we all know, is designed to go around the backside of the moon and then return to the Earth. So you're going to get some great views of the Earth starting off. And if you look carefully, you'll notice sort of the green fuzz right near the edge of the Earth on the top.
Ah, yes. There.
You see that? And also on the bottom. So on the top, it's not completely at the exact top. It's off to the right a little bit. And then down below, it's off to the left a little bit. And that's both the northern on the top right a little and the southern lights.
Yeah, the auroras.
The auroras were out at the time when they launched on Wednesday. So that's really cool. And that's not surprising because in the last podcast, we talked about space weather. And there was a coronal mass ejection, remember, just prior to launch.
Right. And so the Earth's magnetic field is still ringing.
And yeah, that's what energized it to have these, northern and southern lights viewable at the time that they did launch last Wednesday. So
Yeah.
that's an added benefit of that.
I'd seen this picture, but I hadn't noticed that. But yeah, there's those two little slathers of green. I think you've got the orientation wrong though.
Oh, that'd be the
North
southerns
is-
at the top. I see
Yeah,
that.
I think north is to the bottom of
You're
this
right.
image.
I was just looking at see where the land masses are. So if you look
Yeah.
at the land
That's
masses,
West Africa.
that's right, and you can see the Mediterranean is in the bottom left
Yeah.
of the image. That's right. So there'd be southern lights at the top, northern lights at the bottom.
Right.
Duh. In space, up and down are the same, Robert. What
Right.
does it mean?
They're meaningless.
It-
So,
I mean,
yeah.
when you look through a standard telescope, everything's upside down, anyways, right?
Right.
So,
So yeah. In fact, I've heard plenty of comments on that it's blowing people's mind. Wait a minute, why didn't they turn it right side up? And it's like, why? Up and down only means something when you're on the surface of a body like Earth.
I mean, and that's really recognizable when you look at the moon through a standard telescope.
Yeah.
The moon is upside down.
Right.
Because why make it right side up? Because you have to add an extra optical element like a diagonal or something,
Absorbs and
which
diffracts
absorbs light and
causes other problems.
In fact, if you look at a star, who cares if it's upside down or rotated 33.5 degrees?
Because it's a dot.
Yeah, it's a pinpoint of light, so it doesn't really matter. Anyway, so that's kind of cool, that image for sure.
Absolutely.
And then the next image is when they're much further away, so they're definitely on their way to the moon. So at some point, you go into Earth orbit, check out the equipment, make sure everything is working. In fact, some people argued that maybe this is all they should have done. They should have went in Earth orbit for 10 days so
Right.
that if an emergency happened, because this is the first time there have been humans on this spacecraft, it's brand new.
Mm-hmm.
And if anything happened, dramatic, like something bad, then they're easy to bring down.
Right.
If something happens and you're at the distance of the moon,
You're 3 days away.
yeah, so that can be a real issue, obviously, as we know from Apollo 13, for example. But anyways, that step was skipped. And in some sense, we like to compare it to Apollo, as I mentioned already today. And so the Apollo 7 mission is when they went into Earth orbit and checked out the Apollo spacecraft for the first time.
And they even tested out the lunar lander, didn't they?
No, there was no lander.
Okay.
The lander wasn't ready, almost like what's going on now.
Right.
There's a lot of similarities, believe it or not. And so in Apollo 8, that's when they decided to do the fly around the moon. But they didn't just fly around the moon, they went in orbit around the moon.
Right.
So they had to do the extra dangerous thing of burning the engine to slow them down to go into lunar orbit. But then you're trapped in orbit around the moon if the engine no longer works.
Right.
And thankfully, as we know, the engine did work. And then you get out of the orbit of the moon and head back to Earth again. So that's kind of, we skipped Apollo 7 in some sense. We went right to Apollo 8.
Yeah.
Now, the next flight is Artemis 3, and that's supposed to carry up one or more landers. So, I don't know how that's going to work. I assume only one lander can go inside the Artemis rocket. And so maybe you could send up another one in an unmanned rocket much earlier, have that in orbit around the Earth, in the orbit that you're going to go into.
Right.
And then you can rendezvous with that other lander and basically test rendezvous, right? How to do that.
Yeah.
And also, attach and detach the landers and then get inside the landers and detach it from the main Orion spacecraft, fly them around a little bit, see how they handled with the propulsion system that they have on board. Do all the things that they did finally in Apollo 9. And then Apollo 10, they actually went, within like 50,000 feet of the surface of the moon to test everything and then came back to the Earth. Well, in this case, what they're thinking is by the time we get to Artemis 4, it's a direct landing rather than doing Apollo 10.
Right.
And I know reading the history of the Apollo program, there was a lot of people saying we should have just went right to the landing on Apollo 10. We didn't need to. But that's in hindsight.
Right.
If you would have had some major problems, then you're glad you did that test and not actually land on the surface.
Yeah.
This kind of thing. So you never know.
They back then they were a little more adherent to the plan.
Well, don't forget there was a deadline, right, that you had to meet. And that deadline, obviously, is you had to land on the moon before the end of the 60s.
Decade. Yep.
And that came directly from John F. Kennedy.
Right.
So you don't have that deadline now, per se. You have deadline, of course, where other countries like China want to land on the moon, and they're scared that if they land on the moon, they'll claim their land. That's ours, right? You know, there are different ways. You can't land here. And by the way, we landed on the South Pole, the only area on the moon which potentially could have water below the surface. So they have all of that valuable resources. I think that's what the politicians and the the administration who are leading the Artemis project are having back of their minds. Obviously, is that.
And I can see the point because, there's another way of getting water on the moon, because you can electrolyze out the oxygen out of the silicate, out of the rock itself, combined with the hydrogen simply from the solar wind or the other silicates.
So how much energy would that take?
It takes a crap load.
Okay, so they're talking about putting up a nuclear power plant on the moon too,
Right.
and that's what
That's what I'm saying. When you start talking about that, or large scale solar panels, you take away that energy issue, okay? But does it take a lot of energy? Absolutely, but you can do it,
Yeah, anyways, so that's definitely something they're looking at, because that's. It was a Sean Duffy who was the acting NASA administrator before Jared Isaacman took over, and he mentioned that one of the things they want to do is put a fission nuclear reactor on the moon as soon as possible, like by 2030, essentially. And I think that's
a little ambitious.
Well, I think you could probably make some kind of nuclear device like that.
Right.
And it's just a matter of, do we use it in Antarctica or do we use it on the moon?
Right.
That's just transport it to a different locale than what you're used to thinking.
Is it a Type 4 molten salt reactor, or
I don't know the details.
Type 3 that we've been using, water reactor that we've been using for decades now, and is inefficient.
Well, you're thinking about what is one way generating power immediately is solar panels.
Right.
If you could design some kind of solar panel that would survive the lunar environment, spread it out, and the worry there, of course, it would get covered by lunar dust over time. And there's electrostatic field on the moon, so you have to worry about the buildup of charge. So a lot of things you have to.
Yeah.
I mean, that's why we're going back to the moon. We didn't learn everything in Apollo.
Right.
In some sense, Apollo whetted our appetite. Now let's go do the real work.
Right.
So, anyways.
But NASA made the mistake of making rocket launches seem too routine, and that did not help them.
I mean, the other thing you can worry about too is during that time there was a war going on, Vietnam. Why is it, Robert? Because we've been like close to the moon twice. Mm-hmm. Okay? And each time there's like a war. The United States is involved in a major war.
I don't know.
This time, of course, is in Iran, and last time it was Vietnam.
Right.
Is there any connection there? Like, what the heck is going on with that?
I'm not the one to ask. I would say it looks a little suspicious, but...
Because right away people think, well, we spent so much money on Vietnam and stuff, we couldn't really afford to continue on after Apollo 17. Let's shut the program down. Let's find a cheaper way to get to space, i.e. space shuttle. That's kind of how that went.
And this time we're in another Cold War. We're in a standoff with China. So.
And the other thing is the SLS rocket itself. You ask somebody how much does it cost per launch, they can't give you a straight number. And I've heard estimates from $4 billion to $14 billion a launch.
Per launch?
Per launch.
Holy cow!
Let's take the lower number. Right? I don't believe the 14 billion number, but let's take the lower number. $4 billion a launch. You can't go a lot to the moon for $4 billion a launch.
Yeah.
And they're trying to launch every 6 months, so that's $8 billion a year plus everything else on top of that.
Now, I will point out to you and me and the average person out there, $4 billion. Holy crap, that's a lot of money. You got to remember that the 2026 federal budget is, I think, $7 trillion. So we're not even talking 0.1%.
You know how old I am, Robert?
How long? How old?
I'm so old, I remember when the budget of the United States, I think it was Ronald Reagan, you can probably correct me if I'm wrong, just hit $1 trillion.
Yep.
To run the government. I believe that was under Reagan.
I think you're right.
And now we're at $7 trillion.
We're at $7 trillion.
And plus we borrow, so really is it really $10 trillion?
Uh,
I don't know.
From what I was looking up, I think that's actually the where it's at,
Yeah.
including all the borrowing and everything else.
Okay. And the money we have to pay back on interest,
Yeah,
all that's tied in.
and that's the part that kills you.
And the way I'm sort of hesitating on the 4 billion number is we could buy a Falcon Heavy rocket from SpaceX for what? It was last time I checked, it was like $100 and some million.
Right.
So how many of them could you get? You could literally get 40 of them for the price of one SLS launch.
And this is why I will agree with anybody. NASA ought to be getting out of the launch business. It really should. I know everybody likes seeing NASA rockets go up, but NASA should be getting out of the launch business, and it should be strictly research and kind of the FAA of launch. They assign launch windows.
I wouldn't even do that.
You know?
I think all that should be handled by some government agency other than NASA. I think what NASA should be doing
Fair.
is looking in the advancement of stuff like advanced propulsion. What about nuclear propulsion?
Right.
Right.
I
What about
would
matter,
agree.
antimatter drives? Right.
Mm-hmm.
And then the unmanned exploration of the
Absolutely.
solar system. Let's concentrate more on that. Right.
Let's get science done.
Let's get probes on the surface of various moons on Jupiter and Saturn and Uranus and Neptune and
agree.
beyond. Let's land on a bunch of asteroids. Let's go way out in the Kuiper Belt. Let's hitch a ride to comets and stuff. Every one of them are ready to go and pounce on them. And let's explore the surface of Venus and stay there for a long period of time.
Right.
All of these things can be
I'm
done,
all
and
for
NASA's great at that. I mean,
It
they've
is.
shown that. You know, look at all the stuff, for example, JPL has been involved with over the years. I think that's what we should do. And then for the Artemis project, going back to the moon, yeah, that's a worthy cause, in my opinion, but I'm only one person. And this is a joke, you know, you talk to people and they seem to, everyone has got like, oh, I designed or I was part of the Artemis Well, we're all part of, if you live in the United States of America, you are part of the Artemis project. You can tell that to anybody. I'm a part of the project. And they'll turn around and look at you and say, what do you mean you're part of the project? I pay my taxes.
Right.
Assuming you do, of course. So you are part of the Artemis project. You help fund the whole darn thing. And if it wasn't for the average taxpayer, this is not going to happen.
Right. No. Yeah.
So NASA should be, you know, or the government should be breaking up these kind of missions into smaller pieces so we can launch them on things like the Falcon Heavy and send equipment to the moon ahead of time. And then astronauts get sent there with a lander, right? You can launch a lander in orbit on one flight, and you can launch the main capsule on another one. They rendezvous together and on the way to the moon, land on the surface of the moon and start assembling this material together.
And I will point out that makes sense from the other perspective too, because when you send up rockets to have the equipment and then send up the personnel, you take out all the life support and comfort, the ergonomic weight factors, and you can put that much more equipment into the launch, which brings down the cost. So, yeah.
And the thing is in all of this is that they want to do this, right? They want to launch this vehicle, like I said, every 6 months if they can. Well, right now it's like 2.5, 3 years between launches.
Yeah.
So they already mentioned, the administrator of NASA, that they need to hire a lot more civil servants, like people to work for them to make this. It just seems a crazy way of doing business. It really, it's not sustainable at all.
It's not. And the same thing happened with the space shuttle. They were going to go for launches every month.
Every 2 weeks initially.
And when they actually started launching, they realized that the staffing costs were prohibitive. You know, they always say things, oh, we want to launch at this rate and this cadence. And it's like, but you're never going to reach that cadence.
The space shuttle is a beautiful example of that. It was sold to Congress. That and you can look up the documents from back in the late 60s, early 70s on this, that the idea was one space shuttle, let's say, would land. It would take 7 days, a week, to turn it around, and then 7 days to get it ready to put it on the launch pad and then go up again.
Right.
So it would be ready to go every week or 2 weeks. That was the idea. And we never even came close to that. In fact, when we tried to get close to it, you know what year was scheduled? Looking at the scheduling, right, of the shuttle launches, Guess what year had the most scheduled flights of the space shuttle system?
I kind of want to say, 84?
Close, but no cigar.
Okay.
I don't condone smoking, by the way.
Right.
Just a saying.
I'm not going to take another guess, but
I'll
know
say
that was kind of
okay.
where
I'll
the
say
peak
the year
was.
to you,
Okay.
and you tell me the significance of this year for the space program.
Okay.
1986.
86. Well, that would have been when Challenger
Exactly.
blew up.
Challenger
Yeah.
blew up in January 28th of 1986.
Yeah.
That was the year they were supposed to launch a record number of shuttle. So they were pushing and pushing and pushing. And that all came out in the Rogers Commission when they
Right.
investigated what actually happened. And not only was the technical thing about the O-rings exposed to cold and they became rigid and weren't expanding to fill up the gaps and the grooves where the segments of the solid rocket boosters were mated together and they had a leak, a blow out there, but also scheduling problem. There was a real push on the schedule because that's how it was sold too. And
Yeah.
the more times you launch it per year, the cheaper it is per launch.
Right.
But you well went over the ability of the whole space program. The people who work directly on these equipment, right, went well beyond what they could handle.
Yeah. And then I'll sit there and add, I mean, it's becoming less of an argument these days because we're all holding on to our cars. But I used to point out to people that complained about it. I was like, how long were these shuttles going? And it was like, by that point, it was like, what, 15 years? Right around that?
81 was the first launch.
Okay. But I was like, how many of you keep your cars for that long? And how much more complicated is this thing than your car?
Well, I mean, all the stuff we say it's rocket science, but it's really rocket engineering.
Yes.
And this rocket engineering, I mean, they had a lot of problems. And the two major things that you could focus on were the development of the space shuttle main engines because of reusability.
Yeah.
Right? You didn't have to just run them once and then throw the whole thing into like it dumped in the ocean. You didn't have to worry about it or whatever, or end up throwing in the museum, whatever you get back. Right? And the other thing was the tile system on board the shuttle because of the reusability of the space shuttle itself, the orbiter.
Yeah.
And that had to go, come back, get refurbished, and go back up again. And those tiles are very fragile, as we learned.
Right.
If you hit something like a baseball and throw out a tile, you break it all to pieces. But those tiles is what separates the spacecraft from 6,000 degree Fahrenheit heat or whatever the number is, right?
Yeah.
It's, and that's what keeps it from burning up. Like I said, we've gone down this road and we know the consequence of all that.
Right.
In that sense, it was a poor design because the ice coming off the external tank can hit the shuttle, the bottom
right.
parts of the shuttle, and destroy the tiles, and
Right.
or go through the wing as what happened in Columbia.
Mm-hmm.
And that was, I've seen designs that were done before we settled onto what we actually did for the space shuttle, where you had the orbit on the very top of the stack.
Ah.
Now, if it's at the very top, there's no way for ice to come off the tank and hit it because it's below it.
Right.
So you'd never have that problem. But of course, it's probably a lot more expensive. There's a lot of mass at the top.
You're
Seems to
even more of
me
an
the
inverted
center of
pendulum. Yeah.
center of mass is offset, and it makes it more difficult from an engineering point of view. And the rule of thumb: if it's difficult from an engineering point of view, it takes a lot of money to correct it.
Right.
Simplify the engineering if you want to keep the costs down.
Yep.
And in the 1970s, doesn't seem to be a lot of money floating around either.
Right. So, yeah.
Yeah, so this image anyways is of the Earth as the Orion capsule has already, lit up the engine. And the engine, did you notice where that engine came from, by the way? Do you know the story behind that?
I don't know.
It's one of the OMS engines from the space shuttle.
Oh, okay.
So that's what they use as the main engine on the European service module. So that's the burn, the trans-lunar injection burn.
Okay.
That's the burn that we would use like to slow down and get into orbit around the moon for the Artemis, let's say, 4 and 5 missions, and then to break orbit and come back to the Earth. Now, the OMS engine is interesting. You know why?
No.
It runs on hypergolic fluid,
Oh, right. You
which
told me
means,
that, yeah.
the oxidizer and the fuel are such that they ignite on contact. You do not need a spark, so there's less of an issue or something may go wrong. As soon as the two fluids meet each other, immediately they combust.
There you go.
But it's hard to handle that stuff, as you can imagine.
I
Yeah.
remember my first time being told about that type of thing, and I was like, oh, no, thank you. No, thank you, please.
But they got a lot of experience. They've been dealing with this stuff for decades. So
I mean, hydrazine is bad enough. And you want something that ignites on contact?
it reminds me a little bit about in the future when we have, hopefully, we'll see, matter antimatter drives.
Right.
And thou shalt not, there should be a rule, like another commandment, thou shalt not let matter and antimatter annihilate in the same place.
Right.
That's a dangerous as you know what. But there was a story about antimatter. Do you want to say that? You mentioned it there the other.
Yeah. It's a possibility now that we could have an antimatter drive. Because I forget which country it was, or if it was just the EU in general, but they successfully transported antimatter, which is mind-boggling because you've got to have it in a vacuum. You can't let it come into contact with any material. So they had to sit there and have this in an evacuated magnetic bottle, for lack of a better term.
Yeah, didn't they transport like a distance like 10 kilometers or something like that?
It was crazy.
I noticed the story after you mentioned, I think, on the last podcast about it. So that's only going to get better and better as time goes on. We develop the technology. So, yeah. And the next slide, move on a little bit. Speaking about the OMS engine, there it is. There's the view of it. That's that large nozzle you see in the center. That's the OMS engine. So this was actually, one of two that are used on the space shuttle orbiters. So it's kind of interesting. And, of course, you can see the image of the Earth there is getting a lot closer to the moon itself. A lot of beautiful views, external cameras, which is something that, the technology was different back in the 60s, but it would be nice to have a lot more of those external cameras. And that's kind of a norm now. I'm trying to think, was it SpaceX that had the first external camera? I don't know if they did a lot of...
I don't think so.
I don't think so. I think NASA and other
NASA
companies,
did that.
the Air Force and so on, when they launched unmanned rockets, they had cameras. They just didn't show things in real time.
Right.
But they had a way of collecting the data.
Because I remember on one of the space shuttles, there was a bat one time that hitched a ride.
Well, yeah, they did have cameras. What am I talking about? They definitely had cameras on board the space shuttle. And later on, were showing launches live, right? You could go to the camera. So that technology, evolved to the point where yes, we're definitely going to show you more images.
Yes.
Definitely. So we
ought to move forward. Because,
we got down into this this rabbit hole.
Yeah.
So anyways, very interesting in that sense.
Right.
Now, the next image is of the Earth also out of the window on board the Orion capsule. And you get appreciation for how small the Earth is, and you're at the distance essentially of the moon itself. So about, 240-some thousand miles away.
Right.
So it's incredible when you think about it. And everyone says, oh, I'm on the spaceship. But, everybody on the Earth is also on the spaceship Earth. And you get a real appreciation for that description when you look at an image like this.
Yeah, and here we go with, where are the stars? Exposure times, people. Stars are dim.
Yeah, well, we'll show you that here in a second on another image. Now, speaking about the moon, here's an image of the moon out of one of the windows, too, on the Orion spacecraft. And you can see that it's bright enough that you don't need to dim the internal lights to be able to get a decent view of the moon itself. Mm-hmm. And the way this view is, the face of the moon that's pointed towards the spacecraft is almost fully illuminated. Right. And notice it's mostly the near side, and you can tell that by looking at the dark shading, the Maria, the C's on the moon, as we'd say. And a little bit of the near side, the far side, is also visible in this image itself. So this is not the view you get from the Earth. Right, at all. You see too much of the far side of the moon in this view. So your perspective then
is neat, that two-faced nature of the moon, where it's basalt that faces us, but it's andesite and so forth that are on the far side.
Yeah, and then of course you ask, why is that the case? In fact, one of the astronauts yesterday in a press conference explained that they blamed the Earth's gravity from pulling on the molten lava that caused the eruptions to occur on the near side more than on the far side.
Makes sense. Yeah.
But then again, you could always argue as a scientist, I'd question, in the beginning, the moon is not locked with the Earth in that sense, that it keeps the same side. So
Right.
the Earth's gravity would affect all sides of the moon as it rotated. And
Good point.
these lavas are billions of years old, these lava fields. So why
Are they all on one side?
on one side? If
Yeah.
Are we sure that the moon was locked like that, that always pointed one side to the Earth at the time when these volcanic eruptions were occurring? That's another
It's
question.
a good question.
So you can't assume what you see today, it's always been like that.
Right.
Things definitely change. Here's also an image taken yesterday of basically most of the sort of far side of the moon itself. Part of it is in nighttime, so it's in darkness, and the other part you can see is in daylight. But this is definitely in the backside of the moon. And it's taken from a camera that's on board the spacecraft, the external camera.
Mm-hmm.
So you get to see some of the Orion spacecraft as well as the moon itself. So that's a nice view for sure. Here's a beautiful image. This one was just downloaded, must have been overnight, by NASA when the astronauts were sleeping. And these were just released today. So these are of the observations that they made with their various cameras, high definition, when they had gone through closest approach, which is about, 4,000 miles?
Something like that.
4,000 miles from the
Lunar
moon's surface, a little
yeah.
over that. And you get this beautiful view. So what you're seeing there is essentially the far side of the moon. And notice you don't see the seas anywhere. That
Right.
tells you immediately that's the far side of the moon. Either that or it's Mercury if the Earth wasn't there. Right? Because it looks very
You're
similar to
right,
Mercury
yes.
for sure. Yeah, and
And
so
similar size even.
yeah,
So-
and then we see the planet Earth. So that gives you a perspective of this.
and notice the far side is bright. It's lit up.
Yeah,
by
it's
the
not-
sun. The dark side of the moon doesn't exist, folks.
Yeah. In fact, when the moon is new,
Yeah.
like it has to be when there is a total solar eclipse visible from the Earth, the far side of the moon is fully illuminated. Fully illuminated.
Yeah.
There is no dark side of the moon perpetually.
Right.
There is an instant of time. One half of the moon is in sunlight, the other half is in the darkness.
Yeah.
But that changes as the moon rotates in its orbit around the Earth. It's just the time of going around the Earth is the same as its rotation.
Right.
That's why we only see that one side of the moon. And in fact, the moon does more of that. It's a more complicated type of motion.
Oh,
You
yeah.
have what's called nuntations and so on, where you can sometimes see a little bit on one side than you can at other times, and sometimes you can see the other side a little bit more. So there are these sort of
Yep.
effects that occur.
And
So
it's all moments of inertia and
Yeah.
tidal forces and fun stuff.
all that good stuff. Now here's an image that gets back to what you were talking about. You can't see the stars, right? And people complain about that. Oh, it must be fake. No, it's not fake.
Right.
Here's an image taken from the far side of the moon, right? Just after they went through, the close approach and stuff, the next thing that they done is that there was an eclipse. That is, the moon blocked the sun's light, and that's what we're seeing here.
And lo and behold,
And look what you can see all in that frame. Not only can you see other stars, you can actually make out some galaxies.
yes. And you can make out part of the corona of the sun and all of these nice, wonderful features, but it's because thanks to the moon not being lit up and in the way, they can lengthen that exposure time and the dim objects can now be seen.
Exactly. And that's why you can see all the other stuff around. So these are the images I think people were begging for in the Apollo program. Why
Right.
can't we? Well, the surface is extremely bright. You wouldn't think of it, but it is. And
Right.
to a camera, if you're just recording, it's completely saturated. You're not going to see anything. And the focus was to look at the surface of the moon during the Apollo program. It wasn't to photograph the stars.
The stars.
In fact, they took a portable telescope that operated in the ultraviolet. And you can
neat.
actually go and search for the data that was gathered by that telescope, and you can see images of the galaxies, like the Whirlpool galaxy, M51, taken in the ultraviolet from the surface of the moon by the Apollo program, by the
Beautiful.
astronauts. So the stuff is there. You just got to know where to look for it.
You just got to go looking for
Yeah.
it.
But this is definitely a beautiful, beautiful image,
yeah.
for sure.
Lovely.
Now, for what's going to happen afterwards, well, in some sense, is complete the continuation, I should say, of the checkout of the spacecraft itself. The major thing coming up is obviously going to be reentry through the atmosphere, And that's going to occur splashdown estimated now for Friday. And the last time I noticed it's going to be about 7:07 p.m. Central Daylight Time in the evening. And this is important because there was a bit of a controversy. We like to bring up, things when we hear things.
Right.
And the controversy itself is when the first Artemis 1 vehicle went around the moon and came back and re-entered, the heat shield showed more deterioration than what they expected. Now, people sensationalize a lot of this stuff and say, oh my God, if there were people on board, were they close to burning up and all? No, they weren't. Right? And they have done things to change things a bit. There's only so much you could do because the Artemis II Orion spacecraft was already in production. And so they're going to change a little bit of how they come in to try to minimize more of the heating effect.
And come in at a shallower angle.
That hopefully will alleviate a lot of these issues. So they have done things. Obviously, that's a number one consideration. You don't want to do all of this and then have the astronauts burn up on reentry.
Yeah.
This kind of thing. That'd be enough to kill the program, obviously. It'd be terrible. So they've done everything they could to make sure that will not happen. I have full confidence that, in fact, people look at this stuff and they give a go-ahead or not. Is it ready to be launched? And the answer is yes. People looked at it in depth, right? And so they're the experts we have to rely on. They got as far as they got now as being experts.
Because they know what they're doing.
And so
Does
we
that
can...
mean mistakes won't happen? No, but they know what they're doing.
They know what they're doing. So the reentry then is going to occur then on this Friday evening. So that'll be pretty cool to see. And notice the splashdown. It's kind of like SpaceX in a sense with the Dragon capsules. They're splashing down just off of California if the weather stays good. And it's nearby. It's not like you're splashing down in the middle of the Pacific or the Atlantic and then you got to spend several days on board an aircraft carrier to get somewhere, get to a landmass like the United States or something, right? So it's really convenient.
Yeah, I got to admit, I couldn't tell if it were splashing down in the Pacific, the Baja, California, the little bay or whatever there, or the Gulf.
Yeah, so just off of California, Southern California. So that's pretty cool. And, you could probably land it in Lake Superior?
Probably could, yeah. I don't know I want to try Erie, but,
I don't know. I don't see why. I'm sure it's precise enough you could do that.
Yeah.
And we have the modern computers and now that have onboard thrusters for a little bit, at least helps you with the alignment. You get the perfect alignment coming in.
And let's face it,
Superior,
unlike what a lot of people think, Superior is big enough that you don't have to be that precise.
Yeah. So I think, and we know physics enough, and we brought down how many capsules if you think of all the SpaceX launches and so on and so forth. And so we got the physics of it worked out pretty well, if you ask me. So really cool.
Absolutely. I mean, I'm sitting here saying I don't like rockets. I don't like watching the launches and everything. But these pictures and everything after are fascinating. So.
Yeah. Now, talking about Artemis 4 and 5, here you go, Robert. There are 9 potential sites that have been selected now for the first landing.
I don't know that I like any of those.
All of them are near the South Pole because that is an area where, like we mentioned already, there could potentially be ice, water ice, trapped underneath the regolith.
Uneven topography, too.
And it's interesting you say that. Back in the Apollo program, people get tired of me saying that. They did a lot of things. They had a Ranger spacecraft that crash land on the moon. They just took high-speed photos and transmit them right away in real time. And the last one you got was just barely above the surface, essentially, to get some detailed images of the different potential landing sites. And they had Surveyor spacecraft actually land on the moon and analyze soil. In fact, a famous one was Apollo 12 landed right near a Surveyor spacecraft and brought back some of the equipment. I think it was the camera, if not mistaken, from the vehicle itself. That's the one where they analyzed it when they got back to Earth and found bacteria that had been on the camera to begin with that went to the moon, stayed there for several months, and then was still alive when they brought it back to Earth.
Yep.
So it survived. It reminds me of those water bears or whatever they are?
Tardigrades.
Yeah, they could probably handle that too, I'm sure.
Oh,
right?
yeah.
But anyways, so you never and what they realized was when you actually get there in real time to see it, you don't really have a good idea what it's like. until you're really there.
really
In
there.
fact, if you look at some of the landings, some of them are a little tilted, and there was a limit. You couldn't be tilted over a certain amount, or you'd never be able to get off the surface with the old lunar module.
Like,
So-
I'm looking at this and I'm going, this is probably an MRO image.
Yeah, I would sue.
Okay.
Yeah.
So
Lunar Reconnaissance Orbiter image.
that resolution, all those objects are on the order of a few tens of meters in size. So we're talking your garage for any of the rocks or boulders that you're seeing. And they're talking about dropping them in that. I get why they want to, but
And there's a neat optical effect, especially on the crater that's on sort of to the very right edge there, near the, not quite at the bottom, but just below center on the right. If you look at it a certain way, it looks like it's coming out the floor. It's like a plateau. If you strain your eyes and then close and look away and come back again, then it looks like it's down.
yeah.
Isn't that weird how your eyes play that trick on you?
Yeah, it's the same type of thing. Those masks of Einstein, they're actually concave. They're turned in, but your brain doesn't like faces that are turned in. So most people see it as normal face, and it's the same type of effect going on. Your brain really doesn't like seeing things that are at depth.
That's why it's important to have like LiDAR or something to measure the height of the features with a laser or something, get accurate numbers rather than trying to do it visually, because you might get caught in that kind of situation.
And it's a real. The Apollo astronauts talked about it, and it's because there's so little. There's no trees. There's no bushes. There's so little to give you an indication of perspective.
Yeah.
When you're coming into the moon.
It almost reminds me a little bit about stereoscopic glasses. Mm-hmm. And you look through them, and sometimes you don't see it. Like they don't overlap perfectly.
Right.
And you got to let your eyes just kind of relax and your mind not to think about it, then open them up, and all of a sudden you see the three-dimensional effect.
Yep.
It's the same kind of thing, right?
It is a similar effect, yes.
Yeah, that's pretty cool. Anyway, so these are 9 potential landing sites. As far as we know, they could change their mind, of course, but this is what we're looking at. And it's all obviously clustered around the South Pole for the reason we described already. So that'll be interesting. And notice there's not a lot of good real estate to land on, you would think. A lot of it's treacherous.
Yeah.
So whatever lander they select, it better be robust enough to be able to land in not in a flat area, but a hilly area, and be able to then take off again, on some of an angle or whatever.
I mean, that's caused problems with the Japanese and India, their missions that they sent to the moon recently, right?
Yeah.
They ended up turned over.
Yeah, that's because the center of mass was too high. Yeah.
And the topography was too uneven, and floop, off it goes.
I know. Maybe you could design a lander that has a hydraulic system.
That's what I'm thinking.
That would change the tilt of the ascent stage that's going to leave the lunar surface, right? Mm-hmm. And that way you can line it up better, make it more horizontal.
Yeah.
So,
and then you could drop down and have like landing skids instead of pogo sticks.
Yeah, exactly. The flexibility, the leg length would change.
Right.
To compensate for. It's like walking on the side of a hill or something, right?
Exactly.
With one leg longer than the other.
That's exactly what I'm thinking of.
So we'll see how this plays out, but there you go. That's the latest on that. Okay, so we're going to change a little bit, get away from the Artemis mission, and talk about something very interesting that also happened on the weekend. And this is Comet C 2026 A1 maps. Now, this was the comet. This is part of the podcast that we showed a couple of weeks back, where the prediction was the comet would make a close approach to the sun and back out the other side. That's the trajectory that you see there in the slide. And then somewhere around April, sort of the 6th, 7th, 8th, 9th time frame, the comet would appear just after the sunset. It would be in the evening sky in the twilight, but the comet would be so bright that you could easily see it with the unaided eye. It would be a fantastic sight.
Yep.
And they were talking about, numbers where the comet would be extremely bright. In some cases, I see numbers we're predicting almost as bright as the full moon. So that would have been cool to see that.
Cool. I seriously doubt it would have gotten that bright, but yeah, it would have been cool.
Now, we know that brightness predictions of comets historically have been awful.
Yes.
So we take them with a grain of sand when you think of a comet. And
Yeah.
so you got to be very careful on all this, and not get too amped up, if you like, as they say nowadays, over
Right.
all this stuff. And in fact, that was the case for this comet. If we go to the next slide, what we discovered was the comet did survive. This is a movie of data taken from the Soho telescope, space telescope,
Wonderful mission.
which is observing the sun. Now, the size of the sun itself, its physical size, which is about a half a degree from our location here on Earth, is that white circle you see in the center. And then you see there's sort of a disc-like structure near the center. That's because if you allowed the direct sunlight to go in the instrument, it would burn it out. It's too bright.
Yep.
So they just put this occulting disc, as we call it, in front of the sun to block out that bright light, essentially the photosphere of the sun, and a little bit beyond. And what you see in the bottom left then is the incoming comet. And notice that before it goes behind the occulting disk, so before it even reaches the sun, it gets stretched out dramatically.
Right.
So the gravitational tidal field of the sun is tearing that comet to pieces. Now, in general, a comet is a loose collection of material. And they vary from comet to comet. They're not all exactly the same. And so this comet then had a certain, if you want to call it, a tensile strength, if you like. But it wasn't strong enough to prevent its breakup as it got near the sun. In fact, if you keep watching the movie clip, after the comet itself disappears, look in the sort of the upper right, and you see this puff of white that goes away from the sun. That's the leftover debris of the comet.
Yeah. It did not hit the sun, mind
No,
you.
it did not hit the
Okay.
sun.
But it was going so fast, falling in that close to the sun. It was going so fast, and it made that tight curve around the sun. And on top of that, it's moving through those tidal fields, as you mentioned, that rapidly. It just got torn apart.
Yeah, it's
which
really
is what
cool.
we were expecting. I'm sorry to say, folks, but yeah, we've seen this happen.
Yeah, for sure. So, I mean, if you're interested in this kind of stuff, if you like science,
Yep.
if you like math, if you like physics, if you like geology, if
Absolutely.
you like, any of this kind of stuff, even if you like to write about it, and we always need community, who's going to write about the Artemis mission and get the facts right?
And get the facts right.
That's the thing we always gripe about, right?
Right.
It's, all these kind of things.
I get it. They want clicks on their website.
Well,
but come on.
Exactly. Come
Throw us a
on.
bone.
So you could go to places like the University of North Dakota. It's a really great place
Yes.
to learn more beyond the high school level, to do higher education. We have both online courses and on-campus courses, and you can take even both hybrid courses, right? You can do a
Absolutely.
little of both. It's all up to you, and lots of flexibility. Unlike when I was getting my undergrad,
Where you had to be there.
you had to be there, and it was like a one-track thing. You had to follow that, and that was it. There was really no flexibility. That's not like that nowadays. And one of the things as an educator, like we are, is we
Right.
always try to improve how we teach, how we transfer
If
knowledge
you're good at the job.
from
anyway.
us
Yeah.
to the next generation. And it's not stagnant, right? We're always trying to do that sort of thing and do it in the right way.
Yes.
So yeah, University of North Dakota is the place to be. And summer will soon be here, and it's a beautiful time to visit our campus.
It
If you're
is.
planning on going, to university after high school and you're in grade 10 or 11 now, we invite all of you, come visit us.
Come see us.
Come see what we're all about. And we have a brand new STEM building that will soon be appearing here. They're doing the
Right.
foundation now. And there's all kinds of other exciting things going on at the university. And our hockey team is in the Frozen Four. So that comes up later this week.
Is that really what they call it?
Yeah, that's the Frozen
Wow.
Four. So we have a chance of winning the whole thing starting the end of this week. So there's lots of stuff going on related to the University of North Dakota. So
Yes.
please give us a look for sure.
Absolutely.
Okay, Robert,
Okay. What
we're at the end of the podcast.
Okay.
Our next podcast will be a week from Tuesday. That would be April the 14th. And then the following week, April the 21st, we do have our very, very special guest, Dr. Andrew Knoll from the Harvard University, the paleontologist. He will be here. He wasn't able to make it today, which was the initial kind of thing that we had set up.
And this type of thing happens.
Yes,
So.
but we will have him 2 weeks from today. So please stay tuned for that for sure. That will be very, very interesting.
Yep.
He's written several books, and one of which I've read not too long ago. And very good, very interesting. So we'll have lots of questions. Should be a great conversations for sure. Now, Robert, we always leave you with a quote.
With a quote.
Now, everybody, please listen up. This is really cool. At least to me, it's cool. Hopefully, you'll feel the same way. James Lovell, or Jim Lovell, was the commander of Apollo 13.
Right.
He also was part of Apollo 8 that went around the moon for the first time.
Okay, I
which
did
is
not know that.
which is similar to
What we just did.
what we had just done with the Artemis II mission. Now, Jim Lovell, he passed away back in August.
Mm-hmm.
He reached the good old age of 97.
Nice.
Good life.
Yes.
A lot of things interesting he had done in his life. A life well lived, for sure.
Right. Agreed.
Prior to his death, he recorded a message for the Artemis II crew.
Oh, nice.
What
Cool.
whoever thought of this, my hat's off to you.
Right.
This is amazing. And they played the message to the crew yesterday morning as they were about to go behind the moon.
Sweet.
And here's the radio transmission from NASA to the crew of Artemis II from Jim Lovell. Hello, Artemis II. This is Apollo astronaut Jim Lovell. Welcome to my old neighborhood. When Frank Borman and Bill Anders and I orbited the moon on Apollo 8, we got humanity's first close-up look of the moon and got a view of the home planet that inspired and united people around the world. I'm proud to pass that torch on to you as you swing around the moon and lay the groundwork for missions to Mars for the benefit of all. It's a historic day, and I know how busy you'll be, but don't forget to enjoy the view. So Reed, Victor, Christina, and Jeremy, and all the great team supporting you, good luck and Godspeed from all of us here on the good earth.
Nice. I'm not surprised. A lot of those Apollo astronauts were showboats, but they were pretty cool gentlemen. So
very interesting. So if you like this podcast, as I mentioned, please give us a thumbs up. Subscribe if you haven't subscribed, and we'll see you next time.
later
Thank
on,
you.
folks.